In this video, we are going to discuss the breadth first search or BFS traversal. First of all, what is traversal? Traversal is the process of visiting each vertex in a graph. So let's say if this is the graph and these are the vertices, then visiting each of these vertices but only once, that is known as traversal. In breadth first search, we start at some selected vertex, which is known as the source or the starting vertex of the graph. It could be any vertex of this particular graph. You can choose any node to begin with. We move horizontally and visit all the vertices of the current layer. So that means from the starting node, we will visit its neighbors, and then after visiting the neighbors, then we move to the vertices of the next depth level. We will use a queue data structure for traversal. Queue, as we know, is a first in, first out FIFO data structure. So all the adjacent unvisited nodes of the current level, they will be pushed into this queue. These nodes will be marked as visited because we have already visited or explored these nodes, and one by one they will be popped from the queue. Now the graph may contain cycles and it is possible that we come back to the same vertex again. This has to be avoided because in traversal we have to ensure that each vertex is visited only once. So it is important to track which vertices have been visited, and we can mark them as visited, not visited, or explored, not explored. So if we start from this node, and if we explore its neighbors, then we have been to 1, 3 and 2. Who is a neighbor? Any node which shares an edge with another node is known as its neighbor. So it is adjacent to this node and is having an edge with it. So from 0 we can see 1, 3 and 2 are its neighbors, but when we come at 1, there is a possibility that we may go to 3 again, but we have to ensure that we do not visit a node which has already been explored earlier. So let's take an example and see how the BFS traversal works. We take a queue data structure which is initially empty, and this is a graph, and we can see that there are 7 vertices over here. What we do is we take any starting node. So in this example, we are taking 0 as the starting node, but it could be any starting node, 4, 5, 2, any starting node we can take, and we will push this vertex or the starting node in the queue and we will mark it visited. So if we have front was over here, so we have put 0 over here at the front, and then this will shift to this and we will mark this node 0 as visited. After that, whatever was at the front of the queue, we will remove it from the queue and visit the unvisited neighbors of that particular node. So this was the node that we started with. If we see what are the neighbors are 1, 4 and 3. So this is a neighbor, this is a neighbor and this is a neighbor, and these are having edges with the node 0. We will push these neighbors into the queue. So we have pushed these neighbors into the queue and we will mark these nodes as visited. Also, since 0 has been removed, so after all this operation, we will see that 0 has been removed from the queue and we can print it also. The front of the queue is now pointing to node 1. Now we will visit all the nodes which are adjacent to 1 but have not been visited earlier. So if we look at node 1, and when we are pushing these nodes earlier, 1, 3 and 4, they can be any order. It could be 4, 3, 1, it could be 3, 4, 1, or it could be any order. So when we remove 1 from the queue, because that was at the front of the queue, so we have to remove this node and we have to visit all the unvisited neighbors of 1. Which are the unvisited neighbors of 1? 0, 2, and 4. 0 has already been marked visited. 4 has already been marked visited. So now we insert 2 into the queue. So there is an edge over here, and now we have inserted 2 also in the queue. So after this whole operation, this is what the graph looks like, that 0 and 1 have been popped out of the queue and 2 has been inserted in the queue. Since 1 was also popped out, we can have it printed also. Now the front of the queue is pointing to node 3. So this is our node 3. If we check the neighbors of node 3, it is 0, 1 and 4. 0, 1 and 4, they have already been marked as visited. So there is no new neighbor that needs to be put into the queue. So we will simply print print 3, and 3 is also has been removed from the queue. So we are just left with 4 and 2 in the queue. Now we will remove 4 from the queue because that is at the front of the queue, and we will check the neighbors of this node 4. So neighbors of node 4 are 0, 1, 3, 2 and 5. Out of these we see that 0 has been marked as visited, 1 has been marked as visited, 3 has been marked as visited, 2 has been marked as visited. So the only neighbor that is still unvisited is 5. So we will insert 5 into the queue and also mark 5 as visited. We will also print 4 because it has been popped out of the queue. Now the front of the queue has node 2. So we are at node 2. We have to now visit all unvisited neighbors of 2. If we check the neighbors of 2, it is 1, 4, 5 and 6. 1 is already visited, 4 is visited, 5 is visited. Only unvisited neighbor is 6. So 6 is inserted into the queue, and since 2 has been popped out, so 2 is also printed over here. Now the front of the queue is pointing to node 5, and we check the unvisited neighbors of node 5. So if we see, we have 2, 4 and 6. Out of these, 2 and 4 are already visited, 6 is also visited. So now we don't have to put any new node over here, and we can simply pop out. Since the node has already been popped out of the queue, we can print it, and now the front of the queue is pointing to node 6. Node 6 does not have any additional unvisited neighbor, so it is also popped out and printed. If we look how the levels are being marked, we started from node 0. The next level nodes were 3, 4 and 2. So these are forming one level. When we reached 1, we saw that the next level node was 2, and from 4 we saw that the next level node was 5. So these are forming another level. So from the first level, whichever were the unvisited nodes at the next level, they form the next level, and this forms the third level. So you can figure out the levels of the nodes also, and these may change depending upon the starting node. Also, when we see how the edges have been, how the neighbors have been panned out, we see that if we remove the edges from the neighbors which were already visited earlier, this gives us the minimum spanning tree. Also, the time complexity of this algorithm is order of V plus E, where V is the number of vertices and E is the number of edges. V is the number of vertices, that means this decides how many vertices we have to visit it, and E decides the neighbors because edge gives the definition of the adjacency or the neighborhood. If we look at the pseudocode of this breadth first search algorithm, so we have this breadth first search algorithm given a graph and some starting node. This could be any starting node S. and for each vertex V in VG. So VG is our array of the vertices of the graph. So for each vertex in this set or this array of vertices, we will create an array, explode V, and we will put false for all of these vertices. That means all the vertices are initially unexplored. So they are not visited. So explode, we said, is another term for visited. So initially, because none of the vertices are explored, so they have been marked as false. Now since we have taken one starting node, now we will put a true value, or so this is explode is a Boolean array. So this will have either false or true. So for all vertices which have been visited, we will mark them as true, and all those which are unvisited, it is still false. So in this array of explode, for this particular starting node, we will mark it as true. We take another Q. We take a Q which is initialized with S. So initially we will put S at the front of the Q, and we have already marked it as visited over here. Now while this particular Q, which is our data structures, as long as it is not null, we will do the following. We will run this loop. We will take the vertex from the front of the Q and remove it from the Q, which is also known as the dequeue operation, and we are referring to that particular vertex as U. So initially, right now at the front is S, so we will remove it from the Q. This is our U now currently, and for each V which is adjacent to U, so now that means we have to find out whatever are the neighbors of this particular node U. So let's say that was neighbor N1 and N2. So we will put all those vertices in the Q. So if they are not explored, so only for vertices which are not explored, we will put them in the Q, and we will mark them as explored. So explode, for that, those particular nodes will now become true, and we will insert all these vertices at the end of the Q. So now for each of the neighbors we do this. Next, when we come to this which is from the front of the Q, again we will check the unvisited neighbors of this particular node N1. Now U will become N1, and whichever are the not explored neighbors of this U, now they will be added to the end of the Q, which is your NQ operation. So this we keep on doing till and we keep on popping out nodes from the front of the Q and inserting their neighbors to the Q, and this we keep on doing till our Q becomes empty. So this is the pseudo code of the breadth first search algorithm.